Hello everyone. Today we're going to talk about section 8.1, which is on similar polygons. So last lesson we had talked about section 8.0, which was a little introduction to some ratios and some proportions. We're going to use a lot of that information that we saw in that section again for this lesson right here, but we're going to take it a little bit further and include a little bit more geometry. So the geometry concept that we're going to talk about today is called similar polygons. Similar polygons are going to be two shapes or two figures, and they're going to be considered similar if two major criteria are met. So specifically, if corresponding angles are congruent and if corresponding side lengths are proportional. So these are not the exact same term twice in a row. So what is true for angles? They need to match up perfectly right next to each other, but the side lengths don't. So let's make that a little bit clearer. If you take a look at our two triangles that we see here, you can clearly see that there is one larger triangle and one smaller triangle. Because of that, we're going to have some specific characteristics. Let's talk about angles for a second. We have an angle A right here that is a particular size, and there is an angle D that is the exact same size. They're both acute angles. They would have the exact same numerical value. We have an angle B that is right up here, and that matches up with angle E. They are once again going to be the exact numerical values. And lastly, we have angle C, which is right down here, and it matches up with angle F, which is right over here, and they would once again match up to be the exact same numerical values. The side lengths are clearly not the same. The distance from A to B is not the same as the distance from D to E. A to B is shorter and D to E is much longer. But the way that they relate to each other is with a ratio or a proportion. So if you take a look right here, what you're going to see is that if you take the ratio of side lengths, DE over AB, they are going to be equivalent to another ratio of EF over BC. EF and BC. Now you can definitely tell that these sides correspond with each other. AB and DE are both the shortest sides in each triangle, and EF and BC are medium length sides in each triangle, but they're certainly not matching pairs. So that's an interesting piece right there. I want you to also notice that if you take any of these ratios and you reduce them, that is going to be equivalent to our K value, which is something that Ms. Gums had used in our 8.0 lesson as well. Let's take that little idea and extend it a little bit further. Corresponding lengths in similar polygons. Theorem right here. If two polygons are similar, then the ratio of any two corresponding lengths in a polygon is equal to the scale factor, which we call K of a similar polygon. So that is our fancy name that we're going to use for K. This is called the scale factor, and we can use that in order to go from our smaller triangle to our bigger triangle, or vice versa, from our bigger triangle to our smaller triangle. That is going to be the amount of growing or shrinking that we need to do. We're going to call it K. We're going to call it the scale factor. Let's take a look at an example problem. So our example for our first one right here is pretty simple. I want you to notice how much great information I have given you. I want you to notice that I've given you lots of information about side lengths. They're all labeled clearly, and I've given you lots of information about angle measures. Now, I haven't given you as much angle information. If you take a look, we only have two sets of matching angles, a single arc angle set right here and right here. And we also have a double arc angle set matching right here at the top and right down here at the bottom. That is pretty good. You can actually extend that a little bit further, though, to a third set of angles, which are going to be right here and right here. This is from the third angle theorem. So third angle theorem says that if you already know two sets that match, then the third one has got to match as well, and that's true here. Let's talk about side lengths, though, because that's what the question is about. It says determine whether the polygons are similar. If so, write the similarity statement. So we already know that we have three sets of congruent angles, which is important because that's our first criteria. Second piece is going to be about proportional sides. So I want to look at my side lengths. I'm going to start from my smallest sides and I'm going to go up to my largest sides. So for my first triangle right here, the smallest side is 6. And for my second triangle right here, I have a smallest side of 4.5. Yes, I have another 6 over here, but that's not smallest. So I need to make sure that I'm going from smallest to smallest, not from 6 to 6. That doesn't matter. When I'm looking at this is a good ratio, and we can spend some more time with it, but let's see if we can find some more. Let's go on to medium lengths. So my medium length side for my first triangle is 8, and my medium length for my second triangle is the 6. Now, these fractions don't look the same. That is an interesting fact. But if you take them a little bit further, you will find out that they connect. But let's continue on to our largest sides. On my first triangle, my largest side is 12. And on my second triangle, my largest side is 9. Okay, so now what do I mean when I say take this further? So now that we have our three pieces, what you can do is you can do two things. Thing number one is you can divide to get a decimal version, which is something that you might want to do. When you do that, what you're going to find is that all of your decimals are going to turn out to look the exact same. Even though the fractions don't look the same to begin with, the decimals certainly do. So that is a wonderful thing that lets you know that they are all proportional, that they're all matching. Second thing that is going to be important is you want to simplify your ratios. So you have three ratios right here. They all have common factors and you can simplify them all down. When you simplify them, they will all simplify down to the exact same value. They will simplify down to 4/3. 12 over 9 has common factors of 3. 3 times 4 is 12 and 3 times 3 is 9. Same thing for 8 over 6 and 6 over 4.5. They all reduce down to this guy right here. This is our scale factor. This is our K value. It is consistent all the way across the map, which means we can say, yes, we do have similar triangles. Because they're similar, let's see if we can write a similarity statement. My first triangle right here, I'm going to call this triangle LMN. I'm just following alphabetical order. And my second triangle, it would be great if we could follow alphabetical order as well. So let's take a look and just make sure we flow once again, following the same angles and side lengths. This one is a little bit less clear, so let me see if I can clarify it for you. That is going to be side R right there, hard to read. Let's see if we can put our pieces in the right spot. When we went from L to M, we were starting here at our double tick, and then we went down to our single, and we went across our medium length side. I want to do the same thing over here from my double to my single and across my medium length side. So I'm going to go from R to P. When we went from M to N, we were going from our single to our triple, and we were going across our shortest side. I'm going to go from my single to my triple, and I want to go across my shortest side. I'm going to go P and then O. That is our two similarity statements. Take a look at our similarity sign right here. This is an important fact. It looks similar to a congruent sign, except it's missing that equal sign underneath. It is just the squiggly part right there in the middle. Let's see if we can use the same kind of technique right here to find some missing sides. What I have right here is I've got two figures that are known to be similar. You can see that statement right there. And what we want to do is we want to see if we can find this missing side piece right here, which is going to be X. So our question is twofold. It says, what is the scale factor? And then find the value of X. And that's because those are the two major steps that we need to go through. That's a hint for you. It's not trying to make the problem extra long. It's trying to help you get to the final result. So let's start off by finding that scale factor, that value for K. So now when you're finding your value for K, as we saw in the last problem, you can do it based off of any ratio of sides. So just pick two sides that you can feel confident are going to be a match set. So you could pick some medium length sides or some very, very short sides. Whatever is going to feel best to you. You can pick any sides you want, as long as they have numbers that match up on both figures. So I'm going to choose to go with my 20 and my 16. These are a bit longer and people tend to spot them a little bit more easily. You don't have to. Also, I want you to notice that I'm choosing to do 20 over 16. You don't have to do that either. You could put 16 over 20. It is really up to you. Whatever makes you feel good is what makes me feel good. So just do whatever is going to be best for you. Reducing fractions is important. So I'm going to write this as 5 over 4. This is now going to be my scale factor and I can use this. Okay, so now let's see if we can put it to work. To find our missing side length, which is X right there, we want to build a ratio that is going to be equivalent to our scale factor 5 over 4 that we have. And we want to see if we can utilize the X and its corresponding side. So the two sides that are going to correspond once again are that X and then this 40. These are the longest sides on each figure. And so I want to build a ratio using them. When I built my first ratio, I went from 20 and then 16. I went from the left figure to the right figure. I went in this direction. And I want to do the same thing here. So I'm not going to start with my X. I'm going to start with the 40 and then I'm going to end with the X. So it is going to be 40 over X like so. Okay, now we can solve this proportion just like we did yesterday. And so I'm going to use my cross multiplication skills to multiply on these two diagonals. This isn't the only technique that we saw in each and every one of my classes last lesson. There were people who chose to use different techniques other than cross multiplication. So by all means, feel free to use whatever technique you feel most comfortable with, but cross multiplication is usually a popular choice. And so that's the one that I'm going to choose because I know that it satisfies the situation and it works really nicely and quickly. So there's our answer right there of 32. Your turn. See if you can try the next one out on your own. Once again, start by making the scale factor and then see if you can find the missing side length. I'm going to build my scale factor right here using some of these shorter side lengths on the outer edge. Now you could use the full piece from T all the way down to R, which would be 12. And then you could go from X to Z, which would be 16. But I just chose to use these smaller pieces right here and here. And it doesn't matter. They all reduce down to the same scale factor of 3/4. Then after that, I built myself a proportion. I've used my scale factor. And then I also wanted to use my X and my 20, which are these two altitudes that I have inside of my picture right there. I'm going to create that by going once again from left to right. And so I'm going to have my X over 20. Then I'm going to cross multiply and solve. For both of these cases right here, it is great to kind of determine if what your answer has is reasonable. For my first answer, I got 32, and that is smaller than the 40 it is compared against, and that's good because X was on a smaller shape. Same thing's happening here. I got the answer of 15, which is shorter than 20, and that makes sense because my X value looks like it's shorter than that 20. So I like my answer. It seems reasonable, and I want to keep it. Once you've done fiddling around with side lengths, it makes sense to kind of take that a little bit further. So we're going to take that on to perimeter and also area. Let's talk about perimeter for a couple seconds. If you're interested in figuring out about the perimeters of similar figures, you can use this idea right here. Two polygons are similar if the ratio of their perimeters is equal to the ratio of their side lengths. So that means when you are coming up with perimeter, which means you are going to be adding up all of the side lengths as you move completely around the shape, it will follow with that normal ratio that we've been talking about. So this right here represents perimeter, and that is equivalent to any ratio of just a single set of side lengths as well. So it will also produce a scale factor. It all works to produce the same exact value. This is convenient and easy, and it works really, really nicely. You don't have to do anything special. You just continue on with what you've got going already. Here's a problem right here about an Olympic-sized swimming pool. It says a town plans to build a new swimming pool. An Olympic pool is rectangular and has a length of 50 meters and a width of 25 meters. The new pool in the town is shaped like an Olympic swimming pool, but it has a length of only 40 meters, so it's a bit shorter. Find the perimeter of the Olympic pool and the new pool. So I have no idea what the other dimension is for my new pool right here, but I do know that it's similar to an Olympic pool. So I'm going to try to use that to my best of my advantage. So let's see if we can put it to work and get ourselves a decent answer from this. So just like we have in the past, the best thing to do is to start off with a scale factor. So I'm going to start there. I don't have matching side lengths right here for these widths, but I do have matching side lengths for these lengths. So I'm going to use those to build up my scale factor. And I'm also going to reduce my scale factor as well. 40 over 50 reduces down to 4 over 5. Cool. Now, what you could do is you could do exactly what we did on the front side. You could use that to find your missing side length, and then you could calculate some perimeters, and that would work out fine. By all means, feel free to do that, but you don't have to. What you could also do is you could just skip the side length and jump right to perimeter if you want, which is what I'm going to choose to do. So let's talk about perimeter for a couple seconds. We'll be back to the scale factor in a couple moments. So to begin with, what I want to do is I want to see if I can figure out what is the perimeter for our Olympic size swimming pool. This is easy to do. Perimeter in any case is always an addition of all 4 of the sides. So we're going to have our 50 across the bottom and our 25 up the left side and our 50 also across the top and another 25 on the right side as well. And if you add up all of those values together, you are going to end up with a perimeter of 150 meters. Make sure you put some units on there. Okay, so now if you want to do the new pool, once again, you could find that missing side length and get it that way, but I'm not going to. What I'm going to do is I'm going to use my scale factor, which is 4/5. And I know that perimeter is proportional to any side lengths. So I'm going to use my 150 millimeter or meter perimeter that I already had. And I'm going to use that to find out my new perimeter that I am looking for. This is a simple equation. I can now cross multiply. I'm going to do my 4 times 150 and 5 times p. When I cross multiply, I'm going to end up with 5p is equal to 600. I'm going to then divide by 5 on both sides. And when I divide by 5, I'm going to get my p-value, which is going to be the perimeter for my new pool. And the perimeter for my new pool better be smaller because this pool is smaller. And it does turn out to be, it is only 120 meters this time. So this seems very reasonable and it's working the way that it's supposed to, so I feel comfortable about that. Your turn. See if you can try out the same kind of concept right here. Once again, we've got 2 shapes right here, and we need to see if we can figure out some missing pieces. Here is that information. So to begin with, part A says find the ratio that relates the two triangles together. And I've got a note for you here. We have no corresponding sides. So we're going to actually use perimeter to figure out what these two triangles are related to each other. So I'm not really looking at the picture so much. I'm going to be focusing on these two perimeters that we have right up here. And I'm going to build my scale factor based off of them. Now take a look. One of them has a decimal in here. So it does reduce down to 7/4, which is going to be valuable. But another thing that can be helpful in this situation is if you actually double each of those values first. So you can take your 94.5 and double that. And then you can take your 54 and then double that. That will grow the numbers and make them bigger, which is not great, but at least they won't have decimals. Then after that, then you can reduce them down maybe a little bit more comfortably. So that is a good strategy for you to use. For part B right here, we're going to take our new scale factor, which is 7/4, and we're going to use it to see if we can find out about those altitudes. Now, one of the altitudes is given to us on our smaller triangle, which is the 12, and the other altitude is the one that we're trying to find, which is going to be X. So I'm going to make sure that I put my 12, which came from my smaller triangle, with my shorter piece right here, and my mystery side is going to go with the longer 7. When you do that, you're going to end up with an altitude of 21 centimeters. And it makes sense that it should be bigger than 12. And so that feels comfortable to me. All right, so now we found out that sides are proportional and perimeter is proportional as well. The next logical stop is going to be area. So let's take a look at that. Area is slightly different. And so this is one that tends to burn some people. So I want you to make sure you're paying close attention to area so that it doesn't happen to you. Right here for area, it says if two polygons are similar, then the ratio of their areas is equal to the square. Squares are the ratios of the two corresponding sides. So look carefully right here. We've got our side lengths, which are A and B, and you'll notice that we have a ratio built for them. And we also have our two areas, area of figure 1 and figure 2. And I want you to notice right here that they are being squared. That's an important piece right there. We cannot forget about the square. The square is critical. If people get these type of question wrong, it's not because they mess up on the proportions or setting up the ratios. It's because they forget about the power. So that is the most important piece. I want you to make sure that you can keep that in your mind and don't lose it. Let's try some out. So for our first example right here, we have two triangles with very little labeling, but we have just the right amount of information that we need. So it says the polygons are similar and we want to find the area of the unknown. So we're looking for a small area to go with this second triangle that we have right here. Let's start off by building our ratio or our scale factor. So when we're building our scale factor, we're going to use some side lengths in order to do it. We have a 10 and we have a 5. Now you can build that as 10/5 or 5/10. You build it however you want. I'm going to go from left to right. So I'm going to go 10/5. I'm always going to reduce this. That's important to me. Good common factor for this is 5, which is going to reduce this down to 2/1. Always got to be a fraction, so I can't just write it as 2. I'm going to use 2/1. Okay, so now areas should be related to this scale factor as well. So that means we should be able to build ourselves a proportion. When I'm building my proportion, I'm going to use my area of 36. And I'm going to also use a variable to represent my missing area. Okay, so now this is where a lot of people make their mistake. Once again, it is not a direct relationship between side length and area. It is a relationship between the square of side length and area. So we need to add in that power of 2 right there. And once we do that, then we'll be on the right track. So this proportion is going to change slightly, and it's now 4/1 is equal to 36/x. From this point, now we can cross multiply on our diagonals. And we are going to end up with 4x is equal to 36. And we can solve, and we'll end up with an x value of 9. Now remember that this is a area, so that means that our area value is going to be 9 centimeters squared. That power of 2 is critical. You could work the whole problem without using the power of 2, and you'd probably be convinced that what you did was great, but it would be a little bit wrong. And so you would need to make sure that you go back and check that work. Make sure it seems reasonable. This is a small triangle. It should have a small area, and it does, and so I feel comfortable with what I have. Letter B is yours. See if you can try that one out on your own. Similar type situation, we're going to start off with our scale factor based off of our side lengths, which is 7/21, and reduces down to 1/3. Then I'm going to set up a proportion with my 1/3 and my areas. So I'm going to have my 84 and I'm going to have my mystery side length right here. Don't forget about your powers of 2. So I've got my powers of 2 on the side lengths, not on the areas. Then I'm going to set up my proportion with my new fraction 1/9, and I'm going to cross multiply. My larger rectangle should have a larger area, and I end up with an area of 756. That is very big, and I'm feeling confident about that. Our last example is an important one. Our last example is very important because it is going to be a bit backwards. So our last example right here says the ratio of the areas of two similar figures are given. So if you take a look, we are starting with information about two areas. We have information about areas. And what we want to do is we want to write a ratio for the lengths of the corresponding sides. So if you take a look at what we have right here, we've got this ratio, which is 81/121. Okay, so now that is a ratio of areas, and it should be equivalent to a ratio of side lengths if those side lengths are squared. Well, I don't want squared side lengths. It didn't mention squared side lengths. It just said lengths. So that means that what we really want to do is we want to get rid of these powers of 2. And the best way to get rid of a power of 2 is use an opposite operation. The opposite of a power of 2 is a square root. So we are going to be applying square roots to both of these values in order to get a ratio for our side lengths. When you take the square roots for both of these values, the square root of 81 and the square root of 121 are both pretty nice. You end up with 9/11. That is going to be the ratio of the side lengths. So it no longer has to do with any areas. It's not the full figure. It is just the side lengths. It also could be used for perimeter as well. So this right here is going to be the final answer. It is also asking for a ratio. So you don't have to find a particular side length. You just have to find the ratio of any of the side lengths in the figure. And so this guy will suffice for any of those.